mark as done your quiz, please mark as done in your Google Classroom. Okay, so after you mark as done, the quiz can give you directly your score. I think most of I have checked and grade, and you can actually look up the solutions that I upload the solutions on chapter 14 materials. Okay, you can check the Google Classroom. Okay, back to the 14.7, the maximum and minimum value. Basically, what we are going to do is basically similar with the calculus 1. The first thing we need to do is we need to find the critical point in which the local minimum or maximum might take place. And then similarly, we will take second derivative test, but in a different way. Okay, in a different way. Okay, this is example on how we are going to look at on some graphs. Maybe I will start from the next page here. Okay, let me give you this. Okay, if you see here, you will notice that if this is a set of domain, okay, set of domain, the highest one we will call them the absolute maximum. The lowest one is the absolute minimum. And if they have another maximum or minimum in between, we will call them local. Okay. Now, let me give some definition first. Okay. A function f has a local max at some point. If exists disk, okay, so the disk is it's like an interval that we want to observe, okay? Centered at the point that we are going to check, and we have the conclusion such that the function at that point is greater from most of all points x and y. And this is local max. And similarly for local min, if this is less than, okay. And for absolute max, I will just write the key points. This is same thing as local max, but in terms of all domains for all points in domain. And absolute minimum, same thing as local minimum, but in terms of domain. Okay. Okay, that's, I think it's pretty much easy to understand, especially if we are looking at the picture here, right? Okay. The next thing is bounded sets. Okay. So, what bounded sets means? If you have 2 dimensions and you have a curve like a random curve. Bounded set mean any box that you can draw that contain the curve, and from that box you can define which one is your maximum value and minimum value. Okay? In 3 dimensions, we can do this similar bounded sets. What we are doing is we are now making the box into a volume. So you have a set of curve, okay, inside the box. And from this set of box, it's called the bounded sets, we can observe the maximum and minimum value. The bounded sets will be used in some terms and definitions. Okay, for example, in the extreme value theorem, so if the function, this is continuous on a closed and bounded sets, so it's restricted to a box, okay, a certain box. Okay, bounded sets in real number, then function has both absolute max and absolute min. Okay, and then if you remember the Fermat theorem in calculus 1, it's actually similar. Okay. So if functions has a local extreme, either max or min, at a point, let's say the point is x0 and y0, and if the first order of partial derivative f, they exist at this point, then we have a conclusions from the Fermat theorem that our first derivative, in this case our first partials, will be equal 0. So both partial x and partial y should be equal 0. And this is actually our critical point. Right? So we will, maybe not critical point, this need to, this will settle critical point. Okay. That's the first intro for the maximum and minimum value. Okay. I think we can skip that. The next thing is, if you remember this picture here, this is from chapter 12. So this is from quadric surface. This is we call the hyperbolic paraboloid. Right? Now, if we are taking any points from this picture and we want to know which one is maximum value, which one is minimum value. If we take any random points, we can check the value, right? But then, if you see how the surface goes, okay, compare with this, okay, in which this is, I think, easier to follow. You have the absolute maximum here, local maximum here, local minimum here, absolute minimum here, right? In every parabolic or any curve that you can look up, you will find any point there, right? And then you can check whether they are a maximum, minimum, right? But here in this hyperbolic paraboloid, when you are take this point here, what is this point, right? Is it maximum? Is it minimum? And from the chapter 12, I've given you that this term here is called the saddle point, right? In summary, okay, what saddle point means is it's actually not maximum, not minimum, but this is the critical point also, okay? Because it's behave like it goes something having parabola there, right? And having parabola here, but it's having probably like behave like it's having a maximum or minimum, right? But we don't really know in those points. But we can write saddle point. It has partial x 0 and partial y also 0. It's our critical point, right? But it is not maximum or minimum, but we call just saddle point. So we will have at least, okay, at least if you check the quadratic surface, you will have maximum, minimum, and saddle point. Okay, the next thing, what we are going to do is how we can define this maximum, minimum, and saddle point from a functions, okay, from a function. And from here, we will learn the second derivative test in our multivariable calculus. Okay, let f a function, let's say these two variables, okay? And let's set up that the functions is continuous, okay, continuous with continuous second order partial. In some disk that's centered around, let's say we have critical point and let D is the determinant. I will explain later. Let's just write first the formula. So we have this determinant here. And from this determinant, we will have, okay, if determinant is greater than 0, if determinant is less 0, and if determinant is equal 0. We have three possibilities. If determinant is positive, we still to check, okay, the partial x, or if you want partial y is also correct. If this is greater 0, you can choose between partial x or partial y. Okay, choose between this. So this is actually or. It should be less 0. Sorry. Okay, if it is greater 0, this will be local minimum, and if this last 0, this will be local maximum. Okay. Here, if less 0, then the point is a saddle point. So whenever your determinant is negative, then it will be directly saddle point. If it is equal 0, then it's inconclusive. Okay, so back to this determinant here. This is actually we can write in terms of this. The determinant. Okay, right. Okay, actually there are some proof on how we are getting this determinant here. But maybe let me show you how. I think if you have your textbook, you can check the, I think the last part. Yeah, the last part. Okay, this is actually came from, if you remember your directional derivative. So let's say we have directional derivative. This is with direction is u. What we are going to do here, we need to differentiate one more. Okay, differentiate. So we apply directional derivative twice. So we get the second order of partials. Okay. So we can write this. It's du. Okay. So from here, from this directional derivative, we are trying to make another directional derivative. Okay. Or let me write maybe this. And then plus the partial y, and then this is the directional derivative, and then k. Okay, from the equation here, if you are dealing with partial, so first is partial x, and then if we differentiate with respect to x, we get partial x, right? Partial x, x. Okay, so we get this is partial x, x, h, right? And then plus partial x, partial yx from the second one here. And then this is k, and then multiply with h, okay? And then similarly, this part, we get partial x, y, and then h, and then plus partial y, y, k, and then k. And from here, we get partial x h squared. And remember that this partial yx and xy is the same, so we are just adding both of them. So adding okay, we have these expressions now. And to make more interesting, because this is a quadratic equations, we can factorize and make it a complete square. Make it a complete square. So this divided by a, right? B over a. And then plus this is c over a Okay, now we have these expressions, and this here, this is our equation that we want to observe actually. So we need to know which one is positive, negative, and from here, if we change the these signs, whether it's negative or positive, we will change the whole equations, right? We will change the way we look at the directional derivative. Yeah, and you can actually look upon your textbook if you read your textbook. Okay, given that the partial xx on some point is positive and the determinant on some point is positive, but the partial x and determinant are continuous functions, so there is a disk with center of that point itself and radius which is positive, the delta, a small radius, okay, so that the partial xx, it will always positive, and the determinant is positive whenever the point is in the disk. So if you look at the equations, we are going to see that every time this is positive and the d is positive, okay, if this is positive, then this will be positive, right? And we will see that through the concavity, it will have the concave upwards, right? If you imagine the curve and then it will intersect the plane, it will have the concave upward. And if this is negative and this is positive, it will be concave downwards. And from here, from this positive negative signs, we have this conclusions. Okay, we have these conclusions. Okay, hope you get the idea. Okay, it doesn't mean that you need to really understand all these equations or how to relate this equation from directional derivative. Uh, if you understand, that's good for you, but I think in more the essentials part here is you need to understand how, at least how to differentiate this local minimum, local maximum, and the saddle point from the determinant. Okay, I hope you get it. Okay. Okay, maybe we have some example how to find and how to solve the maximum and minimum value. Okay, let's say we have an example that we have a function that is 4xy minus x with power of 4. Okay, maybe it's simple functions first. Okay, find extreme values. So if you are asked to find the extreme value, means you need to find the maximum values, minimum, saddle point, if there is saddle point, or okay. So first, what we can do, we need to find the critical point, right? How to find the critical point? We need to make the partial x is 0. So from here, we get 4y minus 4x cubed is 0. And then the other one is partial y is 0. So we get 4x. And then we need to find x or y. Depends on you. From these two equations, okay? So we have two equations, and we can just substitute or eliminations. Maybe substitute. It's suitable for these cases. For this is this, and we can substitute to here, in which we get the okay. Okay, we equations now. What we are going next. I think because it's power of 8, we can treat this as a quadratic. So we can factorize, and we can factorize one more, right? So from the imaginary part, we can look for the real number, right? So from the real number, we get the x is 0, x is plus minus 1. So we have only this 3x. So is 0. So we have x 0, 1. So I will be -1. Okay, here from here we have now d. We'll write d is partial xx, partial y is partial. Okay. Maybe partial x. Negative 12 x squared, partial y is negative 12 y, and partial x y is 4, or you can write this is equal this and equal 4. Okay. And now we can check all the d that we can find. Check 0, 0. This will be is that's 0, right? It's negative because of negative 16. Because of 4 squared. And then the next part, the d for 1, 1 is positive, and negative 1 also positive, right? because it's having a squared for negative, so it should be the same. So this is the first one. Second one is checking the partial x-axis. So from here, we get, this is no need to find. From 1, 1, we get negative. From the third one is also negative, right? So this is negative, positive. Uh, Maybe I just erase that part. Negative, negative. So this will be the saddle point. So for 0, 0. So 1, 1, and negative 1, negative 1. Both will be local maximum. Okay. Let me go back. Say we have the. It's want to know the point where it's minimum or point. Also check their sensitive. So check the point root secondary. Okay. Okay. Now uh, I think it's found about the absolute. Uh, okay. Okay, wait. Sorry for the lost connection. Yeah. Can you hear my voice? Okay, sorry. I don't know. Let me check. But I don't think it's stable. Oh. Okay, how about now? Is it better? Okay. Sorry. Okay, wait a moment. Okay. Okay, I hope you can see this screen. Okay. The next thing is the absolute maximum and minimum that I want to give you some additional notes. Yeah. So if functions is continuous on closed bounded sets in domain, okay, in real number, and f attain absolute max. If we have x1, y1, and absolute mean at x2 and y2, at some points, okay, indeed the points means the x1, y1, and x2, y2. How to make it happen is basically the same as in local. So first is we need to define the critical point, but in whole domain. Second, the extreme value, meaning we need to take the second derivative test to take to make distinguish between which one is local max, which one is local min, and which one is the saddle point, and evaluate. And then if you have the largest value, this will be your absolute max, and if it is smallest value, this will be your absolute min. Okay. And also you can evaluate the boundary if there's any boundary. Okay. This is just a note for absolute max and min, but actually the all the practical approach will be the same. Okay. Okay. This is actually the end of the chapter 14.7. Okay. One last section in chapter 14 is about the Lagrange multipliers. Okay. 14.8 Lagrange multipliers. Lagrange, we can write Lagrange in terms of the symbol, a lambda, okay, a Greek symbol, to give you some illustrations of what Lagrange means or how we are going to use that. It's actually uh, used for finding the max and minimum value. Okay, max or minimum value. Same thing as 14.7, but this is a specific method to find. Okay, let's say we have a function here. Let's say this is just xy plane, but in terms of 3 dimensions. Okay, so this will be the xy plane, and let's say this function here is functions g. Uh, we have a certain value here that we are sure that it is a constant. Okay. Okay. Then we have another curve, set of curve, lots of them. Okay. Let's say this is a functions of functions, and we also know this is maybe 10, maybe 9, maybe 8, maybe 7. Okay, maybe 6, maybe 5 here. So what we are going to do is actually what we need to find is we need to define, or we need to find this f. Okay, this f is actually we need to determine. So we need to determine this. So f is a function that we want to observe, okay, the extreme value. And or maybe let me write here. So we seek the extreme value of f when the point is restricted on level curve of G. So this basically gives you a sense that we can move this f, okay? We can move this f until it is touching the point on G. So let me draw another color. Okay, maybe that's okay, maybe like that. Okay. The green color is touching the blue one, right? The F is touching the green one. So basically that is when we want to maximize. So to maximize, so we need to finding largest value of, let's say, a constant C of such that that level curve, or let me write here, this is equals C. Okay, such that level curve x, y is equal C will intersect the functions G. Okay, so this G is, we can also think as a constraint, okay? Like a constraint. So restrictions of the functions. Okay? So when this has intersections, meaning it's touching each other, right? What does it mean? It means that the normal line will be identical, right? For both f and g. Normal line f and g will be identical, right? As a consequences, the gradient factor f gradient factor of g, this will be, let me just write that. This will be parallel. And because of this parallel, we can write the gradient factor of f at that point when it's touch each other is equal some constant, some constant c or some constant lambda of the gradient factor g. And this is basically what the Lagrange multipliers method. So the method here, it tells you that if you can find the gradient factor of f and gradient factor of g, and you can find there is a some number, a constant, that are relating these two, which means you can take you can find this point, and you will know that this point will be the extreme value. Okay. Okay, to make it short, let me just give you um, a few examples, of how to use this Lagrange. Okay, it's actually quite practical. Okay, so first, let me write here. Let me write the example. Um, if given that f is, we have these functions now, and as constraint, and it's just saying that use Lagrange multipliers to find the extreme values. Okay, and how we are going to use it? First, this is the function that we want to check max or minimum value, right? From the critical point that we are going to find. And the second one is the constraint. The constraint, we can write the constraint as our g, right? So you can write f. Sorry, this should be three variables. Sorry. So f. Let me just rewrite the function, and we can start. Or maybe I will write the g first. The g will be 3x plus 2y minus 8z. Okay. No need to write the constant because the gradient will be make the constant 0, right? So this is just all the variables that we need. Okay. Now write down the conditions for the Lagrange, that these two should be parallel, right? And having a multipliers. We call this is the Lagrange multiplier here, or the lambda value. Here is in more details for each partials, right? So basically, we are going to break down all three axes, all three partials, okay? And we are going to find the relations between these two and how the multipliers will be, okay? It can be, right? And you can find that the x is half lambda, and the y will be lambda. Here is negative 4z, and then lambda negative a, or z is 2 lambda. Okay, now we have all these three x, y, z value in terms of lambda, right? And remember that we have the constraint here, the constraint. We can substitute to the constraint. So 3 and then half lambda, and then plus 2 lambda, and then minus 8 and then 2 lambda. It should be equal negative 50. And you can calculate lambda is actually 100 divided by 25. It's 4. Okay. When you get lambda is 4, then you get x is 2, y is 4, and z will be 8. And this point here will be our extreme values. And if you check, this is, if you check through the functions from to here, this will be resulting negative 100. And if you compare with other value that you can find, this is actually our minimum value. Or you can say, you can just say this is the extreme value that these functions can get. That's also fine. Okay, this is the first problem that we might have. Okay, so we can just relate and then just substitute, and we have the constraint, we have the critical point, and we can get the extreme value from the Lagrange multipliers. Another case is still the same Lagrange multiplier, similar steps and similar process, but how you relate the problem is probably a little bit different. So example, so if you have a function, let's say x, y, z, and then you have the constraint. Let me just give you direct questions like this first. And then same questions, use Lagrange multipliers to find extreme values. Okay. And still, same thing. This is what you're going to do. And basically, you are making all the x, y, and z for each partials, right? But here's, it depends on the functions. You might to see different steps, okay? So if you check here, it will be yz, and then it's equal lambda and 2x. And this will be xz, and then 8y, lambda and 8y. And this will be xy, and then lambda 32z. Right? Okay, now what we can do, we can try to do the same thing as before, but here I want to solve this as lambda. All will be lambda. So I can take equations from all this. Okay, so I can take this yz, 2x is equal xz, 8y, and xz, 8y is equal xy, 32z. At least I can make these equations, right? The z is canceling each other. So I have 8y squared and 2x squared. And I can take this and becoming this. Okay, same thing here. This will be 32z squared and then 8y squared. For z squared is y squared. Okay, now we are going to look upon our constraint. And similar like before, we can take this x squared plus 4y squared plus 16z squared is equal 48. So x squared, I will take this as 4y squared, and 16z squared is plus 4y squared, right? So I will have y squared is 48 divided by 12, right? And I get this is plus minus 2. So I have y is plus minus 2. So when y squared is 4, then x will be, or x squared is 16, so x is plus minus 4. Z squared is, or 4z squared is 4, so z will be plus minus 1. Okay. And now we have different x, y, z, right? Because we have plus minus. So we have all positive, it can be, or we can take this negative 4 and then positive. Right? And then we can take this if we can take this we can take this also, and then we can take all negative, right? And then this is the functions. So the functions results, the value will be resulting from here. So this is just 8, negative 8, negative 8, negative 8, 8, 8. So it's just having f is 8 and negative 8. We can say that this is the maximum, this is the minimum. Okay. That's basically the Lagrange multipliers. Okay. Okay. Let me give you some notes, or maybe example and then notes. Okay. Okay. So if we have two constraints, let's say h or g, can we still use Lagrange multipliers? We still can use that. So let's say, let me just give you straight example. So if your functions is this, and then you have okay, and use Lagrange multiplier to find extreme values. Okay, the same as what we have done previously. The difference is just we have two constraints. So first, write the gradient factor of f is equal. Let's say this is g, this is h. This is gradient factor g plus gradient factor. Maybe you can write lambda 1 or lambda 2 for the second one, or lambda, and if you read your textbook, I think you have mu, right? And then gradient of h. And The rest is actually quite pretty similar to the previous examples. Okay. So we can just uh, take the partial x. So find all partials. This should be 4. This is 2. 2 lambda plus 0. So lambda is 2. Okay. And partial y. 6. And then for g is 1. So lambda plus 2y. 2y and then mu. Okay. So we have six equal lambda. Lambda is 2. We get from the first one here. We can write 2 here plus 2y mu, and we can write mu is 4 divided by 2, 2 over mu. Okay. The third one, for z is -2. It's 5 lambda plus 4z mu. Lambda is 2, so -2. This is 10. So 4z mu. 4z mu, and then you have -12. So mu or z will be -3 over mu. So we have now y and z, and precisely we have yz here, only y and z, to make it into our constraint. So we can write y squared plus 2z squared equals 22. So this we can write so this will be 4 mu squared plus 18. So mu squared, this is 22, right? So mu squared is 1. So we can have plus minus 1 for mu. And we have another possibility, right? So for mu positive 1, wait a moment. I need to charge this first. Okay. So we have positive 1 and negative 1 for mu. From this positive 1 and negative 1, we will get two different points, right? From the positive 1, we will get y is 2 and z will be -3, right? From here. Right? And for -1, y will be -2, z will be 3. And this will be resulting for different x, right? And from x is from this equation here. So if you calculate, if you try to compute, x will be 7 and x will be -6. So you will get the first one is 7, 2 and -3, and this one -6, -2 and 3. Now we can check the functions. First check this, and second check this. And you will be, oh, sorry. Okay, wait a moment. Okay, sorry for the. Okay, back to these functions. This will be -42, and this will be 46 if you check. And if you compare with maybe other point that you can make out, maybe 1, 1, 1, or maybe 0, 0, 0, to prove that this is true, that this is minimum and this is maximum. So precisely from the Lagrange multipliers, you will get the results of the value, the extreme value, after you get relations between the two gradient factors, okay, with lambda or with lambda and mu. You will get the points, and you check the points, you will get directly the extreme values. Okay. Okay, so sorry for the connections, because I think this week in my place I get the the because there are some outage for the electricity, and yeah, because the company, the type power company, they announce around this week there will be some outage, so I think it will affect the internet connections also. Okay, but I think we can continue a little bit. Okay, so basically from this one, this is 14.8 finished. So chapter 14 is finished up until the Lagrange multipliers. If I have another maybe special notes or another exercise that may be useful for you, I will have it maybe next week. But I think I can go for a little bit, okay, a little bit, just a little bit, for the introduction of chapter 15. Okay, it's about the multiple integrals. Okay, I hope you don't mind, because today is already June, right? Month of June, and because of that, and we need to finish in 3 weeks, more or less. So I think I need to have more time to teach, and also maybe some points I will skip for chapter 15. but at least I will explain the important one. Okay. Okay, let's start a little bit. Okay, so for chapter 15, this is called the multiple integrals. So from calculus 1, what you get is you get this, right? This means in graph, we are evaluating area under curve from x equal a to x equal b, right? Or in graph, maybe let's draw some random graph. Let's say this is A and this is B. And as you remember that we will have this area here. And how we approach the area is we can slice all the area under curve with a rectangle here, a small rectangle, and we define this as a delta x, and when it's really small we can have dx in terms of this, right? And this is actually a multiplication of the rectangle, right? Rectangle area. So we can write the definition is actually the limit as n is going infinity, how many rectangles it is, the n. We can write this is okay, this is the calculus 1, right? Okay, in calculus 1, we are observing the area, right? Now in calculus 2, we have the similar approach, but we are approaching a volume. Okay. So let me write here, given functions of two variables, that is continue and non-negative on region, let's say region R in xy plane. So find the volume of the solid enclosed between surface and xy plane. Okay, what does it mean is we need to find here, we are going to, so if this is let's say this is a surface, okay, this is z equal fxy, and maybe we have let me use the right color, this region R here. So what we are going to do is, based on this region, let me make the region cut into a small square or a small rectangle. And then we are going to map, okay, to mapping this R into our surface. So we are mapping one by one. And then we have a set of a volume. this is a parallel pipe. If you remember the name parallel pipe. So this is, we are mapping mapping R to Z. Okay. And now we got the parallel pipe, right? And the volume of this will be the area of rectangle on R, right? Multiply with height. Let me just write that. Okay. The area of rectangle, let me just write as a delta, because it's cut into pieces and it has many rectangles. So let me write just a delta of A. And the height will be just the functions of xy, right? So we can approach the volume with this. So at least the volume, we can get similar treatment with the calculus 1. It has a limit as n approaching infinity. And we get this. Okay. And this is actually not just I, but it's actually J also, because it has X and Y, right? So this is actually I and also J. So this is not only I, so it's also J. I start from I equal 1 and J equal 1. Okay. And then this is actually I and J also. And long story short, okay, I will explain later, okay, any more details, but you can write this actually in terms of double integral in region R of your functions, and then this will be dA. This can be dy dx or dx dy, depend on your observations. But this will be explained next week. Okay, so I hope you don't mind. We have now coming on the chapter 15, multiple integrals. We will continue next week, but the chapter 14, up until this 14.8, I will maybe give you some exercise, but just wait for my announcement. Maybe tomorrow for Friday. And maybe you can have exercise for this weekend. And I think I will finish up until here. So yeah. Probably next week we will have another small quiz. It can be Monday or Wednesday. It depends on the situations. And the next quiz will be still chapter 14, part 2, because last time it's part 1, so next time will be part 2. So the section will be most of the section in chapter 14. Okay. So that is for next week. And next week I will still continue chapter 15. I hope I can get at least until 40% or 30-40%, and we can finish in maybe 3 weeks. We can finish chapter 15. Okay. Okay. Any questions first? Any questions? We'll stop the recording.